All right, we're going to consider one more example of application of the Euler equation to understand what happens in rigid body motion. In this case, we're going to think about rigid body rotation. So imagine a static fluid that's placed on a turntable, and we will initially have a liquid level that looks like this. We begin to rotate the turntable, and we want to think about what happens to the fluid surface. And what we're going to find is that we'll end up with a result that looks something like this. Fluid is thrown out through acceleration and piles up near the outside edge. And so the velocity field that we want to consider is given here. The velocity is r times omega. In other words, it's a rigid body rotation. And we need to calculate the acceleration. And we already know that the acceleration in a rigid body rotation, which would be the same as the time rate of change of the velocity following a material element, is that as I move around in a circular motion here, I'm changing my velocity. And so the acceleration we've already worked out in the past is given by v theta squared over r, and it's inwardly directed. So it's in the ER, or the minus ER direction, where the base vector here is minus ER, and that's the direction of the acceleration. So with that understood, we can certainly simply apply our Euler equation. So we might write that rho times acceleration is equal to minus the gradients in the pressures plus the gravitational body force on the system. And we'll define that the body force is acting with G acting in the minus Z direction. So if I define Z as positive here and R as positive in this direction, then for this problem, G is once again minus G times EZ. And with that, I can now take this equation that I have here, and I just need to write it out in its three individual component forms. So we can start with the R component, which would say that minus rho times V theta squared over R. Or if we prefer, we could write that as minus rho times R times omega squared. Just by substituting for the velocity field, is equal to minus dp dr, and there's no component of gravity in the r direction. In the theta direction, there's no acceleration, and there's also no pressure gradients in this direction, because when I go around through a full 360 degrees or 2 pi radians, I must come back to the same place that I began. So this certainly tells me that we shouldn't expect that the pressure is a function of theta. And finally, we might write down the expression in Z. There's no acceleration in Z. There is, of course, a pressure variation in Z, though, which comes from the hydrostatic variation. So we write down that the component of G in this direction is this. And so we'll certainly get that, again, we can see that we'll have a hydrostatic balance in the Z direction. So I have three equations that I need to solve, and I need to find the pressure field. Certainly from integrating the first expression, so if I think about this one, when I integrate this one, I have that we'll find that dp by dr is going like rho times r times omega squared. The minus signs will cancel here when I do the integration. So I certainly will get that I should expect that this goes like 1/2 rho r squared times omega squared. And normally we'll think that we'd get a constant of integration, but of course, since we're integrating a partial differential equation, we really should think that this should be plus some function of z. And I can find the function of z by solving this equation for dp by dz. And so when I do that, I'll get 1/2 rho r squared omega squared plus rho g z plus some constant of integration c1. And so we'll need to find, so this is our final expression for how the pressure field looks. And so you can see that there's a parabolic variation of the pressure. As I go out to bigger and bigger values of R, you can see that the pressure is getting bigger and bigger. And to evaluate the constant, all we need to do is we need to pick some point in our system where we'll say that we'll take our datum. And so the natural place to pick is maybe right on the middle here. So let's say that the height at this point is measured to be h. So I can evaluate that. So at r equals 0, then we know that z is equal to h, and at that point the pressure is equal to PA. So when I use that to evaluate the constant, I'll finally get that the pressure as a function of r and z is equal to the atmospheric pressure plus rho g times h minus z plus 1/2 rho omega squared r squared. And that gives me a final expression for the velocity field in this problem. Sorry, the pressure field in this problem. The question is that you might ask is, what is the shape of the surface? So I drew the shape of the surface here. Certainly it looks like it goes like r squared. You can see that as we move out here, the radius looks like it's or the height looks like it's getting bigger and bigger. But the way to really see that is to again calculate what we would call an isobar. So we'd like to ask, what is an isobar? An isobar means a line of constant pressure. So one isobar, for example, is the variation where the pressure is equal to atmospheric pressure. And so I could satisfy this expression. I have to solve this. And you can see that that will immediately give me a relationship that if this is true, this will cancel with this. And this gives me a relationship between these expressions right here. And so along an isobar, dP is equal to 0, which would be given by dP by dr times drs plus dP by dz, which are variations in z, multiplied by steps along here. And so in general, all of the isobars are given by substituting in for the expressions for dP by dr and dP by dz. And you'll find that along an isobar, so a line along a constant pressure, we must have the r times omega squared over g is constant. Or if we'd like to find the expression for the free surface, where the pressure is atmospheric, if I just solve this equation, set these two equal, and solve for this equation, then you can see that what we'll get is that Zs is equal to h plus r squared omega squared over 2g. And so indeed, our free surface has initially a height h, and then increases like r squared. So if we look at our drawing, what that says is that if I think of a little column of fluid near the outside edge here, the pressure is highest down at the bottom corner here, and the height, the extra height of material here is exactly what's needed to get a large pressure here so that it can balance the tendency for fluid to be flung out by the rotational motion. So we found a nice expression for the free surface height. And this is very useful, particularly if you're interested in making mirrors or lenses, because this is a way of making very naturally a parabolic surface just by rotating something at a constant rotation rate. So one example where this idea of using rigid body rotation to make liquid lenses or mirrors is the giant Magellan telescope. This is one of a class of new super-sized giant Earth-based telescopes that's costing somewhere close to $1 billion. And it's being built very, very high in the high desert of Chile, about 2,500 meters above sea level. And at the end of the day, this is going to consist of a very, very large set of mirrors, 7 all in all. Each one is about 8.5 meters across and weighs 17 to 20 tons. And each one of them is polished flat to within about a 20th of the wavelength of light. And then by mounting them like this, they're all going to exist together as one single large parabolic reflector. So the challenge is to make a lens that is of this size and is a perfect parabola or close to a perfect parabola. And so for each of these 8-meter lenses, the way they're being made is by using a rotating turntable like we've just thought about, and taking glass, this is optical quality glass, that's placed on a surface, and then it's going to be placed inside a giant oven and heated up while this turntable is rotated at a steady rate, and then naturally the glass will flow and make a parabolic surface. So I'm going to show a short video that you can find on YouTube that shows how this process is done. So here are the individual pieces of optical quality glass being placed on the surface. It gives you some idea of the scale and also how thin the final mirror is going to be. You might be interested by the hexagonal patterns on the back of that surface, and we'll see what that's for in just a moment. So here's the lid of the oven being closed, and it's brought up to temperature, and then rotated at a rate, and you can see the glass melt in this time-lapse video, and eventually flow out until it produces a parabolic surface. Of course, it's not quite perfect to within the wavelength of light that is needed, and so afterwards then there is a large polishing operation to actually polish down any defects and bring this close to the design. And finally, here is the final mirror, and here's an example of what it looks like having been hoisted up and coated. This gives you a good view of the backside of the mirror, and you can see that on the hexagonal pieces there are actually individual actuators that are shown here, and these are to actually locally adjust the focal length of the mirror to correct for aberrations in the atmosphere. So this is what's called an adaptive optic. But on the other side of this, it's almost a perfect parabola that's been produced by this idea of just rigid body rotation of a liquid to produce a parabolic surface.